Alright, so I'd like you to get the yellow copy of the rubric, a white printed copy that you're going to write on, the lab that does not belong to you or someone that you recognize, and your notes that you've taken from the last 2 peer reviews, all out in front of you. So most IB labs don't have this much data. This was a lot of data, and part of the challenge was to figure out exactly the best way to present it, exactly which variables to choose, and how to process the data. So we're going to look at some of your choices. For personal engagement, it does not necessarily have to be its own section. Some common places that I find personal engagement are in the background section and in the evaluation section, particularly the second block of the little table where you're talking about the method and your choices. For example, choosing the glass evaporating dish over the ceramic evaporating dish, or adjusting your heating time in order to slow it down as you approach constant mass or in response to signs of burning. Things like that would show a personal investment in the lab. The background section would have things like the uses for magnesium sulfate. So if you see any of these types of things, then you're going to give them credit for personal engagement. Very common to get a 2 on personal engagement. It's not super difficult to do. That being said, for the titration lab that's coming up, which will be the first lab I actually grade, it kind of does need to be its own section, or you need to kind of do a pseudo background section, because the only other thing that you're doing for that lab is the calculations part. So you've got to talk about the eggshells and the pesticides and all that separately. So the next section is the exploration section, and the first part of that is giving a research question. So you may see things labeled like research question, purpose, and or aim. So a research question would be phrased as a question. A purpose would specify that you're trying to find the hydration number. The research question is typically phrased, how does the independent variable affect the dependent variable? But if that's what they went with, then underneath that you should see an aim, A-I-M, where they specify that from that correlation they're looking for the hydration number. So the independent variable for this lab, the thing that we actually changed on purpose, data-wise, would be the mass of the hydrate. That would be your 5 levels. That is not what was graphed, and ideally here you would actually explain that connection between what you actually changed and what you ended up graphing on your X and Y axis. So the dependent variable would ideally be then your constant mass, or the mass of the anhydride. Talking about your moles of water and moles of anhydride is great and actually really should be here in this section, but it is also okay to address that part in the background section and here only talk about what masses were actually changed and measured, as long as at some point you do explain how that connects to what you graphed. But that exploration still includes the background section, so it doesn't necessarily have to be in a under the variables label or under the background label. Either one is fine. One thing that is particularly bad is to go ahead and jump to the hydration number being the dependent variable. You're going to determine the hydration number from the relationship between your independent and dependent variables, but you are not directly measuring nor graphing the hydration number, so that is a bad choice for the dependent variable. Controlled variables are something that we tried in Honors Chem for the reaction rate lab. So we talked about how collision theory specifically shows which variables affect reaction rates. So that kind of lays the groundwork here for we need to find things that specifically do affect the hydration number or the masses and moles of your hydrate and anhydrate. So these are some good examples. The amount or type of heat added, consistent heating. We didn't use hot plate, we used Bunsen burners, but same idea. The humidity or reabsorption of moisture, so the cooling time is important. What's not okay is actually talking about the heating time. That actually does not matter, and it would be great later on in the evaluation section if they actually discuss, adjusting the heating time in response to what's going on with their hydrate, whether it needs to be left on longer or taken off more often. It's actually a bad thing to control. You should be adjusting it in response to what's happening, because that time does not matter. It does not change the outcome or change the constant mass. What is going to affect your mass is the time that it's out in the air reabsorbing the moisture. In that section where they're talking about their variables, which, by the way, ideally is in a table, although that would be more of a communication issue if it's very hard to follow. Part of that table should also be how it is controlled. So if humanly possible, you should put a number to it. An example of something you can't put a number to would be like the identity of the reagent or the type of magnesium sulfate. And you should explain then it comes from the same source, it's the exact same nature of the reactant. You can't put a number to that. Using the same scale, digital scale, can't put a number to that. But if you can put a number to it, you should. So hopefully if you mention cooling, or if they mention cooling, then there's a number to how many minutes it was cooled mentioned in the way it was controlled. An example of something going above and beyond is this first part where the experiment was done in the same day to control the humidity. That's great. Specifying that the humidity was 51%, that's awesome. How do you find that? You record the date of the lab and you go to weather.com or something like that. Maybe not .com, but it is possible. That is why you have 2 dates on your cover page. So the background section, if they didn't have some of the stuff we talked about in the independent variables in that part of their report, it should be here. Although you don't see it on this slide, it was on the other slide. So discussing how their choices of variables connect to the things that were graphed has to be somewhere. So here's their last chance. Background generally is definitions, laws, and theories, right? So of course you have to define a hydrate. Some other good definitions are anhydrate, dehydration, and then constant mass is kind of something that needs to be defined. In the theory section or the background section, it should be explained as it is the anhydrate alone once you get to constant mass. And then in the procedure, you should talk about how it needs to be the exact same number within the uncertainty of the scale for 2 or 3 times, whatever you guys went with. But that's all still under exploration, so it doesn't particularly matter where they put which information. The main law behind this lab is the law of conservation of mass, because the mass lost must be the mass of the water, and you use that mass of the water for your calculation and your final answer. For their procedure, the materials list should be alphabetical, although that is communication if they just forgot to put it in ABC order. Things that are really important that are missing would count off on exploration. For example, the goggles, safety goggles. So safety has to be in their materials list and it has to be in their procedure. The procedure should include safety steps other than just put on goggles and put up your hair. It should be a little bit more involved than that. Things like don't leave the Bunsen burner unattended, allowing the dish to cool before bringing it to the scale, wiping the table down. So that brings me to, it should go from setup to cleanup. And the setup can be very simple if they have a good diagram, which is coming up. It can be like set up as shown as figure 1. But if they don't have the correct diagram, then you can't give them credit for the setup if they don't go through the put the wire mesh on the O-ring and put the evaporating dish on top, that whole explanation. If there's not that and there's not a good diagram, then you can't give them the credit for the setup. As far as clean up the lab is not a sufficient direction. It needs to be very specific. You need to talk about wiping down the table, washing your hands, stuff like that. So about the diagram, I know that there's not necessarily always a part of that that's on the IB checklist, but it is really something that you need to include, and it has to be a real picture from the day of the lab, like an actual picture that is labeled. We've talked about this. So if you are having a hard time reading it, a lot of you guys are still having printing issues. That's more of a communication thing. The main thing you're looking for to give them credit for this setup is that you can tell where do you put the hydrate in relation to the Bunsen burner in order to properly dehydrate the hydrate. If you can't tell between the diagram or the procedure, then that's a problem. That's something you're going to hold against them in exploration section. So that will conclude the exploration section. If you want to go ahead and give them a score out of 6. The white rubric is more to guide you. It's like the red questions from the last couple peer reviews in looking for specific things. But as far as your score out of 6 goes, you want to go back to those core sentences on the yellow rubric. How well did they actually define their question, make it focused? Those are the questions. So moving on to the analysis section, first thing I want to do is go over the 2 different plausible methods to get the hydration number. One of them is far better than the other. So the better method would be to make a graph of the moles of anhydrate versus the moles of water and make your slope be moles of water over the moles of anhydrate so that your slope is the hydration number. You create 3 trend lines, average your slopes linearly, and get your final answer. If they did not figure out that that's what they should graph, it is possible that they calculated hydration numbers by averaging. In order for that to be sufficient, they would need 15 hydration numbers to then average, which is still not appropriate data processing, but it is at least sufficient data processing. If they averaged really early, maybe for example finding an average mass or an average moles, and then only graphing that, or only looking at 5 hydration numbers or 3 hydration numbers, that would be insufficient data processing, which is a much bigger problem. Looking at the data table itself, the qualitative data does not necessarily have to be in a table, although of all the labs we do, this is probably the one where it makes the most sense to include it in the table. But you should have both quantitative and qualitative data for it to be sufficient. It should be labeled correctly. Actually, this probably isn't table 1 if they did a table for their controls, but whatever table number it should be labeled. You should be able to tell what the dependent and independent variable are. The quantitative data, raw data, should match the precision of the uncertainty. So it's probably all masses that we're looking at here. The masses should have 2 decimal places. The uncertainty of the scale is plus or minus 0.01. So you should see, even if there's a missing 0, even if the number ends in a 0, it shouldn't become a missing 0. They should type the 0. Since this PowerPoint was made, Word actually got really good at creating tables, so I usually make tables just in the Word document now, because it doesn't have the tendency to eat your zeros and change things on its own. If you are still using Excel to make your tables, it is possible to format your cells to tell it how many decimal places to give it. It's a left click. All right, so I got a lot of questions on this from the rubric, because it is true that you do not have to go through, I collected trial 1, level 1, whereas Bobby collected trial 2, level 3. I don't care who collects what data. What this is referring to is that you should show 2 different things, ideally, with your labels. You should show a getting to constant mass example. And again, this is ideally in a perfect world, superstar lab. You have a table that shows the mass of the empty dish, the mass of the dish with the hydrate, a decrease, a decrease, a decrease. You're showing a few lowering masses, and then you show same mass, same mass, same mass as an example for what the data looks like as you get to constant mass. But you only do that once. Then you show 15 data points, and those trials and levels should ideally, again in a perfect world, include individual masses for the empty dish, the mass of the dish with the hydrate, and the dish with the constant mass. That would be all of the best data you could present. Now, a lot of you ask me, do we really have to go around and collect every single mass of the empty dish? They're mostly the same. If you notice one's like way different than the others, then don't use that one, that kind of thing. So it is okay to make some assumptions. That's the kind of thing that would set you apart from the 5 or the 6 or the 3 versus the 4. But not showing an example of how to get to constant mass kind of keeps you out of that 5 or 6 box on that sentence. So that's what we're getting at here is here's an individual trial versus here's all of that data. So if you are missing significant portions of what I just described, that would count off an analysis. You should have raw data, and then maybe you're building up to the graph and have some more tables afterwards. That's all fine. It should be linear. If it's hard to follow, if it's 17 separate data tables, that's more of a communication issue. So here's an example of a table. Notice how the gram and the uncertainty in grams is separated. That is because we didn't quite fit on all of them. So it would be bad communication to have kind of the plus or minus 0.01 separate from the gram, or the plus or minus separate from the 0.01 grams. So just some examples. Here's another one that shows grams and moles going all the way up to percent error. Now this kind of makes more sense if you're following the method 2, where you're finding separate hydration numbers, where you would include a separate percent error for all of them. If you're doing method 1, I think it makes more sense to do the percent error of the final answer, because you have sufficiently processed the data to get the valid final answer. But if you're doing it all separate, you have to kind of compare the trials. All right, so we're trying to show some calculation examples on the next couple slides. We're going to look at how you would convert mass to moles. If you did method 2, we'll look at the mole ratio. Whatever calculations you're doing, you want to check on their units and their error propagation, or so their uncertainty. You should have 3 sig figs for most of the answers for your calculations, although there may be some examples. You go by least number of sig figs because most of this is multiplication and division. But when you're subtracting out the dish, you go by decimal places. So here's an example of subtracting the dish from the hydrate. So you add your uncertainties when you do that. So your mass of your hydrate should be plus or minus 0.02. A couple people asked about, well, what if we zeroed the scale? But you weren't supposed to zero the scale because you can't zero the scale in the end. And why would you have a different procedure for your initial mass versus all of your other masses? It definitely messes with your uncertainty. Only take off in one place for that. If you've already taken off for having the incorrect uncertainty on their data, then you're not going to take off again here. And you're not, if you do take off here, you're not going to continue to take off going forward. As you convert to moles, that's the third rule where you're using the molar mass as a pure number because it is an exact number, more or less. So your uncertainty from the scale of 0.02, once you subtracted it out, should also be divided by the molar mass. So I want you to actually check their math on at least one of their conversions. Take the 0.02, or if they mess the first part up, take the 0.01, divide that by the molar mass, and see if that's what they have for their uncertainty in moles. You don't have to check both of their conversions. Just check it at least once to make sure that they do know how to do error propagation for pure numbers. This is very similar. You don't really have to do this again because the idea is that you only do one sample calculation for each part. But in this case, since the hydrate and the anhydrate are two different things, it's actually not going to count against them if they showed, again, how to subtract out the mass of the dish and how to convert that, showing what the molar mass is for the magnesium sulfate and getting a new number. You don't have to check their math again. But if they did get the math wrong the first time, I probably would check again so I know just how bad it is. So about the graph, if you actually did the first method, which again was the better method, then your slope should give you the hydration number, and so then you're going to show, and it could be labeled either slope or hydration number at this point, for each trial. What you want to make sure they don't do is say slope and then give the entire trend line equation. The trend line equation gives you y equals mx plus b. The slope is just m. So make sure they have that isolated, and they can label it as the slope or the hydration number as long as eventually they explain that the slope is the hydration number. There is already a lot of math here, so do you have to show averaging of the slopes? No, there's plenty of other things to look at for communication. If they did anyway, that's fine. It's not a big deal. They should also do a percent error calculation. Now, if they did method 1, you can get by with just 1% error calculation on the final answer because it was come to the correct way. However, if you did individual calculations, so whether they have 15, 5, or 3 hydration numbers, they should have separate percent errors if they did it through method 2. So that they can compare those levels or trials. And then you would find an average. So this is more of a method 2 calculation. You would actually calculate a mole ratio. So this should show proper error propagation, showing dividing uncertainty numbers. So you got to convert them to percentages. And again, I would check their math on one of them. And then method 1 or method 2, you're going to have that percent error shown there at the bottom. So this is important to have this information itemized for method 2. I know we kind of looked at a graph, or a table I should say, like this earlier, but if you are doing method 2, you have to give all of the answers or results from the calculations, even though you're only doing one sample calculation. So if a lot of this information is missing, it's a big deal in method 2 because you have to show your moles before you show your mole ratio and so on for each calculation that you're doing. So you show one sample calculation, but you need a table of all of the results. And in a situation where we've got 15 data points, that's a big table with a lot of information. When you do the graph, method 1, you can get by with just having your raw data and then your mass or moles, or actually, ideally, the mass with the dishes separated out would be great, but especially the moles of your anhydrate and water before you plot those on the graph. And then later you would have the slopes and the average. So the graph should have a descriptive title, should have labels, should have units. A lot of this stuff is communication, but if you can't tell what is graphed, that's a big problem for analysis. And since the slope is the answer, not having an equation this time would be a really big deal for analysis. Ideally, you can tell that they thought about error bars. There's a sentence that talks about consideration of uncertainty. So if the uncertainty seems to be well considered, but more or less inconsistent or wrong in different places. The sentence about uncertainty talks about full and appropriate consideration, which means it's basically all right. And then some consideration or little and no consideration. So most people typically fall in the middle, the 3-4 box on uncertainty, especially when you're getting used to how to process the data. So there's always a graph, and this is an example of a relevant graph for method 2. The graph for method 1, of course, is the moles of water versus the anhydrate with your typical slope. You've seen a million of those graphs, but I wanted to show you one using a bar graph. So this would show the different trials and how they got different hydration numbers and how close that is to the correct hydration number. So this would take you into the evaluation section where you can talk about, wait, what's going on with trial 3? That has some huge systematic errors, and it brings you into that entire discussion. Of course, the scatter plot is a much better analysis, but there has to be a graph, and this is something that could help you in evaluation. So still get you the points. What's going to basically count as not having a graph, in my opinion, is if you just throw something in because, well, there's supposed to be a graph. So I see some people graph mass of anhydrate and mass of water, and that's because they looked at the rubric and they saw what the independent variables were supposed to be, threw it on a graph for no reason, and then didn't use that slope or anything to actually conclude anything. So in my opinion, that graph is there for the sake of, well, I'm supposed to have a graph, so let's just throw one in there. It's not there because it actually achieves anything. It has no purpose. Might as well not be there, in my opinion. So if you've got a graph that is completely meaningless, I say grade your communication, look at the uncertainty, did they set their y-intercepts, stuff like that, but it does not help their analysis score in any way, shape, or form. It basically counts like they didn't bother to do a graph. So then you're going to give them a score out of 6 on the analysis section, again following the yellow rubric. You should be starting to see a correlation between a lot of yeses leading you to higher scores and a lot of nos to lower scores, but your end-all be-all of the score will work like last time where you're looking at the yellow rubric. So onto the evaluation section. So the first section of the table, which by the way doesn't necessarily have to be the table, the first section should be the research question, restated. It can match the previous research question or purpose. It just needs to lead off the evaluation section. Then you're going to go into your explanation of your purpose. And unfortunately for this lab, it does more or less mirror what we talked about in the background. For other labs where you make more choices on your procedures, this section will become very different from your background section. But the only choice you really made in this case was about your evaporating dish being glass, and so that should be discussed here. Explain why you're dehydrating, how the glass dish helps conduct heat more evenly, things like that. And then to tie that into the calculation, again, you're going to go back to constant mass to have some kind of theory behind your calculation. All right, the last 2 blocks of the evaluation section should kind of analyze your result. So you should have your hydration numbers with absolute uncertainty. And it should be, if you process the data with method 1 the best way, you should include 3 hydration numbers or your 3 slopes with absolute uncertainty. And you should have your final answer with absolute uncertainty. So really there should ideally be, and clearly identifiable, 4 separate hydration numbers with absolute uncertainty. Your 3 answers and your final answer. And then if you processed it correctly, you only need 1% error. And by the way, no, you don't need an absolute uncertainty, 4% error, just the plain old pure number is fine. If they did 15 hydration numbers, no, you don't need 15 hydration numbers here. Ideally, they told you to find them in table 37 or whatever it is. And then they have their final answer here. And then they're going to talk about the precision or accuracy of this result. And that needs to be tied to systematic or random errors being dominant. That brings us next to the source of error table. But they need to lead into that source of error table in this section, talking about which type of error is indicated by the precision or accuracy or lack thereof. So for the sources of error, or as IB calls them, limitations, you want to think about your procedures. So the heating or the cooling time, one's a good source of error and one's not. The amount of time heated should have been adjusted. Actually, that should have been talked about in the last section where you were looking at the adjustments you made in your procedure. Cooling time, however, really does need to be controlled because hydrates are hygroscopic, meaning they reabsorb moisture from the air. So the amount of time that they're left without going through dehydration, just sitting there exposed to the air, that's going to affect the final answer. So these are the things you want to look at for, are they good sources of error? As far as the mitigation or fix, it does need to be specific and realistic. So if they say that the evaporating dish or choice of glassware was bad, then exactly what improvement would you make to that specific piece of glassware? It can't just be like, choose a different piece of glassware. So a couple of examples for good systematic errors. Again, the cooling that I've mentioned a couple times. So as it reabsorbs water from the air, the mass of the anhydrate would be too high, or the moles of the anhydrate would be too high. So the hydration number would be artificially low. The correction to that would be to use something called a desiccator, or not as efficient, but kind of along the same lines, just a dehumidifier. These things take moisture out of the air, so they're going to lower the humidity and make it absorb less water. Masses also tend to plateaus. This happened to some of you guys in Honors Chem too, where you just get 2 constant masses and then you do it again and it goes down some more. So that was just you not leaving it on the flame long enough for you to actually drive off more water. So you get this false plateau. It's not a human error, especially when the fact that you're trying to get 15 constant masses in one class period. So some of you did go with 2 constant masses being good enough. So then you would fix it and suggest that you would get to constant mass 3 times. So it's not the strongest source of error, but it is valid. Something that you want to be careful about that I see sometimes, because obviously the inconsistent heating or the burning is a problem. What I see a lot of times is people saying that burning causes the mass to be less. This is a violation of law of conservation of mass. Burning does not cause mass loss. What you could talk about instead would be that the chemical change is indicated by the burning or the graying or whatever. And there should ideally be a matching qualitative observation for this if they talk about this. If you want to flip back to that section. If they don't talk about any graying and then all of a sudden it burned, that's a problem, because what evidence do you have that it actually happened? But assuming that they observe some graying and talk about the burning, but then assume that entire mass is anhydrate at the end, well, now we may be using an incorrect molar mass because we assumed the entire thing was magnesium sulfate. So that would be the valid way to present that error. Saying that burning caused mass loss is not valid. It's not a correct interpretation of the problem. Something you absolutely should not see in this table whatsoever is anything related to the scale. You should know to use the same scale over and over again. You should know that the uncertainty of the scale is a very low percentage in relation to the masses that we're dealing with. It's just not a valid source of error. Not using the scale correctly is human error. There's really no way to spin this. Speaking of the scale, a lot of people bring up pressure on the scale, which is not what causes the fluctuation in the scale, first of all. And pressure is not a valid source of error, and by the way, not a valid control either, because pressure only affects gases. Our magnesium sulfate is not a gas. So controlling the pressure or changes in the pressure are completely irrelevant for the lab that we're doing right now. So you're going to give them a score out of 6 following the rubric for the evaluation section, using your answers yes or no to kind of guide you in how well they followed the yellow rubric, but use the yellow rubric to come up with your score. For communication, you are looking at how well they formatted things, and especially how well things are to understand. So things like not labeling tables or not superscripting or subscripting something. That's annoying, and depending on how prevalent it is, then it would really count against them. But the bigger issue is, were you really able to understand what data was collected? Were you really able to understand, did they do method 1 or method 2? Do all of their calculations and all of their graphs actually serve a purpose and drive home their investigation? Does it match? Like, does the research question phrasing actually match the answer? For example, the purpose is to find the hydration number. The hydration number is 7, as opposed to the purpose is to identify the unknown. The unknown is magnesium sulfate heptahydrate. There should be a cohesion throughout the report. The citations, there should be in text parenthetical citations, particularly in the evaluation section and the background section, and then there should also be a references section at the end of the report. So these are all things that affect communication. It's really hard to get a 4 on communication. You're probably looking at a 2 if I had to guess. Depending on how hard it is to communicate. If you had to sit there and stare at their calculations for 10 minutes to figure out what in the heck is going on, they get a 1 and they're lucky to get that. So that brings me to, don't stress about that you're going to give them too low of a score. This is going to be curved in the sense that the high mark kind of sets the bar, but granted that a couple of people will be standouts from that. So the averages for the past 2 class period on the high end, I'm going to make a 17 the perfect score. So after I look at your classes reports, I assume you'll be close to that. So don't feel like you have to give them perfect 6s or anything like that. Give them honest scores, and we'll just continue to improve